of the vector? Can anybody? How would you find the length of the vector? You multiply coherent with its contravariant counterpart. So therefore, length of the vector I can write x mu, is it? So what is that equal to? x0 plus x1 plus x2 plus x3, is it? So now tell me, what is x0? Ct. And what is this x0? Ct. So it is c square t square. x1, what is this x1 lower? So it is this thing. So this is x0, x1, x2, x3. Is it? What is x1 lower? It's minus x, is it? What is x1 upper? Plus x. So it will be minus x square. This will be minus, what this is? So what is this? Length in, so this is length of the vector. So where? In Mainkowiski space, is it? Clear? So much on? Got it? So much on? Okay. So I can write this very length like this thing. So you can put this x mu, say like in this fashion. Let's write g mu nu x mu in this way. Similar, okay, I have put actually both these indices up. So this nu you can contract and this mu will be replaced here, is it? You sure? Clear? So much on this way I can write the length of the vector. Okay? So much. Any problem? So that means in general, okay, I will be using this kind of definition. This will serve as the length of the vector. Okay, now let's go to the. Okay, so let's write in this object ds square, length of the interval. So what it is? Dx square minus dy square minus dz square. Is it? Is that true?
Yes.
Okay, so can I write it in this fashion? Okay, let's write this one vector. Let's write this dx mu as c dt, okay, dx, dy and dz. Is it? So what that is? So I am writing upper one. So it will be dx0 because c dt I am writing x0. Is it? So c dt will be dx0. So what this will be? dx1, dx2, dx3. Okay, what it is called counterpart? Coherent counterpart. So it is like this thing: dx0, dx1, dx2, dx3. So what is that equal to? dx0. Oh, sorry. So it is c dt. So it is minus dx minus dy minus dz because I have just shown you. So there is a sign change in the special components. Okay? Clear? Okay, now let's write the length this very interval. So which implies therefore ds square I can write like this thing: dx mu dx mu. And that is same as dx mu dx mu. Can I write? Can I write? So now multiply. So it is c dt, c square dt square minus dx square minus dy square minus dz square. Is it? You sure? Okay. So what I can write? So or I can write ds square as g mu nu dx mu dx. Clear? Okay. Any question? Any problem? Now let's write the dot product in general in this four-dimensional space-time. Suppose if I am having a 4 vector a mu and another 4 vector b mu, how I can write the dot product? Okay, so it will be, okay, dot product in 4-dimensional space will be simply a mu, b mu, or it will be a mu, b mu, like this thing. Okay, you need to contract the index, and I have said, I have already told you, once you contract the index, the index must be what? One should be upper and other should be lower, which you are contracting. Okay, so this defines you the dot product. Okay, so look here, it is simply the dot product, isn't it? Or isn't it? Are they dot products?
Yes.
What dot product gives me? Length of the vector, is it? So now if you are having in general two vectors, two 4 vectors, so the dot product will be given like this thing. Now let's calculate the dot product A dot B. I will use A dot B. It's actually like this thing, A mu B mu. That is same as actually like this thing, A mu B mu, or I can put it in general, G mu nu A mu B mu. Clear? Okay, so now let's expand this. So let's expand this A mu B mu. So it is A0 B0 plus A1 B1 plus A2 B2 plus A3 B3. Clear? समझ रहे हैं? Clear? Okay. So this I can write simply A0 B0. Can anyone tell me what I can write it? So I should have specified. Okay. So let's write. So you are having this A mu as A0, A1, A2, A3. Okay. So what is B mu? Let's write. So I can have, let's say, B mu as B0, B1, B2. Is it clear? So now if I write this B1 is lower one. Okay, if I started with like these are the positive ones, is it? This B1, okay, so let's assume this B1, B2, B3. When I lower down the index, what it will give me? So it will give me a minus sign, is it? Okay, now look here. What is this A1, B1? So these are the special components, is it? So how we define the dot product in just for 3 vectors? Multiplying by the corresponding components, is it? Is that true? So now if I started this A1 upper, so this B1 lower would have a sign change, is it? So this is this of this form, minus times vector A dot B. Just tell me. So because this will be what? Special component, this is special component, this is special component, is it? So when I put the vector notation, it means I am dotting the special components of the vectors, is it? Clear?
Yes, sir.
Okay, why the minus sign change? Minus sign changes because one index will come with a negative sign, is it? With a change in sign. So this I can write simply like A dot B. Okay? So if it would have been, let's say, Euclidean geometry simply, then we should have a plus sign here. But we are not in the Euclidean geometry, is it? Although the Mainkowiski space is itself a Euclidean geometry, it is a flat geometry, but simply there are the sign changes. Huh? Clear? Okay. Let's define this F4 derivative, partial mu. So it is defined like this thing, partial by partial x mu. Okay? So this is a contravariant one. Eh? Sorry, this is a covariant one. I'm sorry. So index here is upper. So just remember the definition. You are having this thing, and I have put a mu here. Eh? Partial. So the components are like this thing, partial by partial t. If I take partial by partial x, okay, let me write first. So partial by partial x, partial by partial y, partial by partial z. So what is that equal to? So this will be partial by partial x0, partial by partial x1, partial by partial x2, partial by partial x3. Is it? समझ आवा? Clear? Okay, so you can also write this as 1 by c, partial by partial t. What are these things? These are actually the components of the nebula, is it? So I can put nebula here. Okay, so now let me write the upper one. So which gives me upper one simply as partial by partial x mu. So what that will be? That is simply partial by c partial t. So now these will come with a minus change, is it? Utisha? Special components will be having a change in sign. Partial by partial x minus partial by partial y minus partial by partial z. So you can write it like this thing, partial, okay, c partial t minus times nebula. So what is that equal to? It's actually like this thing. Okay, so you can put simply like partial x0, partial x1, partial x2. Okay? Now let's take the dot product between this and this thing. So like this thing, partial mu and partial mu. That is same as partial mu and partial. So what it is? It's a double derivative, is it? So what is that equal to? Partial 2 by partial x mu, partial x mu. You sure? Is it? You sure? Huh? Is it the double derivative? So partial by partial x. Okay, so this is a derivative, act to this. So you will get partial 2 by partial x. Samajh aaga? But mu is one is upper and another is lower. Okay? Clear? Okay, so now let's calculate it. So what I need to take? Just the corresponding components. What is the corresponding? 1 by c partial by partial t, 1 by c partial by. So it will be simply 1 by c square partial 2 by partial t2. Okay, you can simply write, okay, partial 2 by partial x0 plus partial 2 partial x1 partial and so on. Okay, I will not go into those details. So I will just do this. So you are having nabla here and minus nabla here. So it is nabla dot nabla, that's nabla square. So what this operator is called? It is known as D'Alembert. So the box operator. D'Alembert is known as. So it's an operator. It's a double derivative. Okay? Got it? So we'll be using this frequently, this D'Alembert. Okay, so now let me write the general Lorentz transformation. So that will be last thing, because I have to leave early. Okay, so now what is our vector? 4 vector. So we'll consider all the 4 vectors, is it? So we start with some vector for which the components are x mu. It is the muth component of x, is it? So under Lorentz transformation, how they transform? So there is a 4 by 4 matrix acting on the components, is it? So I will write this way. So this is, okay. So let's write. So you start with some x, okay, some components, acting on it some matrix, 4 by 4 matrix. So what it will give me? Some x prime, is it? Teacher? Is this the case? So this will be general. In for the Lorentz boosters, this will be having that 4 by 4 matrix what we are having. Okay, I am writing that. So in general, I can write the components transform this way, x prime mu. So let's write this as this way. Okay? Clear? Huh? So isn't it a 4 by 4 matrix? Mu goes from 0 to 3 and nu goes from 0 to 3. Is that 4 by 4 matrix? You can think this mu to be, let's assume, to be rows, and nu you can think as columns. So samajh aaga? Okay, let's write it this way. So this is a general 4 by 4 matrix. It may contain all entries can be non-zero, all entries can be 0. Okay, then it is simply no transformation at all if all entries are 0. Okay, so let's compare this with the Lorentz boost. So this is a 4 by 4 matrix and it transforms your 4 vector to a new 4 vector. Okay, so let's compare it with the Lorentz boosters. So then you can appreciate what this lambda mu nu is. Okay, so what we are having? Lorentz booster. So I am having x0 prime. Now I am using x0 instead of ct. x1 prime, x2 prime, x3 prime. Okay. So what is this equal to? So it is gamma minus beta gamma 0 0 minus beta gamma gamma 0 0 0 0 1 0 0 0 0 1. Okay. So what this is? So it's x0, x1, x2 and x3. Okay. So now let's compare. Teacher? So let's compare. So this is a 4 by 4 matrix. Okay. So now let's write. So let's write from here. So you are having x0 prime. Let's take mu equal to 0. It's simply 0 nu x nu. Because nu is a dummy index, mu is a free index. Okay. So let's write it. So it's lambda 0 0 x0 plus lambda 0 1 x1 plus lambda 0 2 x2 plus lambda 0 3 x3. Okay. So now let you tell. Now if you take x prime, okay, x0 prime, how many components are with that? X0 and x1 are mixed, is it? What this is a transformation between x and t, is it? No y and z are involved. Clear? Everybody is following it? Good. So now tell me, if I am taking, let's take x0 prime. So what is x0 prime here? Tell me. X0 prime is simply gamma x0 minus beta gamma x1. What are the rest? 0, is it? Now let's compare. So since this is a Lorentz transformation for boosts, so what this lambda 0 0 will be? So I am having x0, is it? x0 is there, is it? Teacher? So what this lambda 0 0 will be? It is simply gamma, okay? Now tell me, what is this lambda 0 1? It is minus beta gamma. So what is this lambda 0 2? 0. Good. What is this thing? 0. Samajh? You got it? You got it? So that means how many components? So these components are 0. Similarly, you can calculate now. Let's take x1 prime as what that will be. Now tell me. So it is x1 0 x0 plus lambda 1 1 x1 plus lambda 1 2 x2 plus lambda 1 3 x3. Now let's write again. So you can write x1 prime here. What is that equal to? Minus beta gamma x0 plus gamma x1. Is that true? So now look here. What is x0 coefficient? Lambda 1 0. X0 coefficient is minus beta gamma. So what you will get? So this is minus beta gamma, is it? So this is gamma. What this object is? 0. What this object is? Similarly, you can now calculate all other coefficients. Okay? Samajh aawa? Samajh aawa? So therefore, if I have to write boosts along x direction, I can say that is simply equal to, if for this very matrix, lambda 0 0 is what? Gamma. Lambda 0 1 is equal to minus beta gamma. Lambda 1 0 is minus beta gamma. Then lambda 1 1 is equal to gamma. And lambda 2 2 is equal to 1. Lambda 3 3 is equal to 1. And rest lambdas are what? 0. So this will define what? Your boost along x direction. Okay? Clear? Huh? You got it? So let's take the space-time diagrams and then next. Okay, tomorrow we'll be finishing this concept. I have to leave.